So all of the integrated rate laws do essentially the same thing. They relate the concentration of whatever, what the reactant is, to time. And that's what makes these things so powerful. So a useful expression, or like a useful way of looking at these things, and we'll look at an example of this. People will talk about rates in terms of half-lives. And so the half-life stuff, it's not really anything new. I mean, there's a little bit more like math involved, or it's just a little bit different in terms of how you treat things quantitatively, but there's still expressions that do essentially the same thing, which is relate time to concentration. That's sort of the big thing that we're trying to do here for kinetics. So yeah, what is a half-life? Let's just start there. So the half-life, this is just the point or the time it takes. It's the time required for the initial concentration. So for us, that's A sub 0. To decrease by 1/2. So what does this mean? That means that if you start out with 100 grams of something and you wait until it gets to 50 grams and you measure the amount of time it took to go from 100 grams to 50 grams, that is the half-life. That is at least the first half-life for whatever reaction you're looking at. To solve this, like to write out the equations for it, well, so let me give you the equations first, and then I'll tell you how to solve for them, just in case you're interested. But really, since what this does is it relates the initial concentration to whatever concentration you're looking at in a sense. So you can write out T1/2. So this is the half-life. So this is the time required for the initial concentration to go to half. For a 0th order reaction, it's going to be equal to A sub 0 divided by 2 times K. And so before I go and write out the other ones, what you'll notice here is that it's still, we're taking time and we're relating it to the initial concentration. And so this expression here of the half-life is really just a re-expression of the integrated rate law, but just kind of talking about it in a very specific way. And we'll look at kind of when that's useful. For a first order reaction, the half-life is equal to 0.693 divided by K. There's some consequences as far as that is concerned. You'll notice that it doesn't actually have the initial concentration in it at all. And then for this one, it's 1 over K times the initial concentration. So second order and 0th order reactions depend on the initial concentration for whatever the half-life is. But you'll notice that the first order is not concentration dependent. It's independent of that. But in order to solve these, like where do these come from? All you have to do is you can take the integrated rate law to derive, let's say, the half-life. All we have to do is substitute this in. So, by definition, we're saying that the half-life is when the initial concentration A sub 0 goes down by 1/2. And so if you come back up and look at the integrated rate law, that means that all you're saying is that A is generally going to be, right, this is the concentration at like time t. And so if we're looking for the time at which we have half of this left over, we can just set A sub t equal to 1/2 of A sub O. and solve, and you end up getting you end up getting these half-life expressions for it. So that's where these come from. They fall right out of the integrated rate law equation. They're not very hard to derive. Yeah, so where do these come in handy at? Let's see. So one place so first order is kind of the interesting one. Let me wrap it into the kind of chemistry type stuff we've been doing. Actually, let's just go with the radioactive stuff. So, yeah, let's do one kind of chemistry oriented problem, and then we'll look at the other thing. So the half-lives, the most common place that you hear about half-lives, right, are in when it refers to radioactivity. So if you've like when the Fukushima thing happened out in Japan and stuff, people will talk about the half-lives of the radionuclides or whatever produced from that. And that just tells you kind of how long they're going to be around. So, a lot of these radioactive isotopes have very long half-lives, and they're emitting lots of gamma rays and stuff. And this is problematic when you're trying to dispose of radioactive waste, like, these nuclear weapons and stuff from the 1960s that we had. Those are just kind of buried or kind of sitting around trying to find a home. They're probably, they try to like bury them out in the mountains and stuff in Nevada. But those things are going to be around for like 1 billion years or something, emitting dangerous radiation. So, but that's related to the half-life. When we talk about radioactive decay, we can talk about it in terms of half-life. Yeah, with respect to chemistry, with respect to some of the chemical kinetics we're doing, let's say that we have a second order reaction. With a rate constant equal to 6.14 times 10 to the minus 2 liters per mole seconds. And that we're describing, let's say the reaction is, we've looked at this reaction before. So we're looking at this dimerization reaction. And then we want to know, so we have a second order reaction with K equals 6.14 times 10 to the minus 2. So what is the half-life? So there's a good amount of ways that you can be asked about half-lives. You can be given the half-life and asked to solve some stuff for it. And I think there's some good problems in the homework for that. So this one is giving you some data here and asking you to calculate what the half-life is. So we need to know also second order reaction, and we'll say that the initial concentration Okay. So we've got an initial concentration of C4H6 of 0.01 molar, and we know what K is. And we want to know what the half-life is. And so the half-life is just expressed in terms of time. So all we have to do is look at the appropriate, so since we know it's second order, we just grab the appropriate equation here, and we want to calculate what T1 half is. And so we know that T1 half is equal to 1 times K times A sub O. And so it really just comes down to plugging in some numbers here. So you'd end up with this, and if we punch that into the calculator, we end up with 1,630 seconds. So what does this mean? Like, what is the half-life? Yeah, I know. So in the homework, they do this first half-life, second half-life, third half-life thing. I think, yeah, in general, you can just assume that it's asking for the first half-life unless it's very specifically saying something like, what's the third half-life? You know, so if it gives you an initial concentration and it just asks what the half-life is, you're generally calculating the first half-life. I think that's generally how these questions are phrased. Yeah, second half-life, third half-life. When I read those homework questions, those kind of threw me. I can show you how to solve for. We can look at that. So let me show you what so this is the first half-life. So generally, the half-life is, so for second order, things get a little weird, or not weird. First order is actually stranger, but the second order, you actually, this concentration, the starting concentration is important. And so let's see. So T1 half, the first half-life, let's say, is 1,630 seconds. So what does that mean? So that means that our initial concentration is just 0.01 molar. So after 1,630 seconds, how much are we going to have left over? I'm not sure how to write that out concisely. Let's just put it down here. We'll have whatever 0.01 is divided by 2, so 0.005 molar. That's all the half-life is. It just tells you, if I'm starting with this, this is the amount of time it takes for that concentration to decrease by half. So for a second order reactions, and this is something I was like, I guess it's not necessarily not obvious, but for second order reactions, this value of A sub O matters. So if this concentration here was much higher, let's say it was 10 molar or something, the half-life is going to be different, right? It's going to be a shorter half-life because we see that A sub O is inside of the half-life expression here. So this is let's say this is the first half-life. The second half-life then, now what you're looking at is the time it takes to go from this new value. So, this is the first time. It took me 1,630 seconds to go to half, which is 0.005. Now I want to know how long is it going to take me to go from that to whatever half of that is. So 0.005 divided by 2, so 0.0025. Yeah, it depends on the order. That is correct. That is what we realized in office hours the other day. All right, so now we're looking at, so this is specific to second order. We're looking at, we can look at a first order one. Yeah, if we have to, we can spend a bunch of time in class on this today. But yeah, so now we want to know what the second half-life is. So now we just use the same equation again, but A sub O is different now. And so this equation just tells me that starting with any concentration, starting with any arbitrary concentration, if I want to know how long it takes to go from that concentration to half, I can use this equation. So A sub O normally, you know, when we're working out with the integrated rate law, it's always going to be whatever the initial concentration is in the reaction. So this is what I think is confusing about this. It's always going to be whatever this initial concentration is. But when you're talking about the half-lives, the initial concentration is sort of contextual. So for the first half-life, yes, it's exactly equal to what the initial concentration is in the overall reaction. But for the second half-life, well, now we're not looking at the initial concentration of the reaction. We're looking at this concentration over here. We're just saying, well, okay, like, so after the first half-life, I'm at 0.005. Now, how long is it going to take for me to go to 0.0025? And so that's just, again, going to be equal to see if I can squeeze it in right here. I don't know why I keep wanting to write the half first. Right, there we go. So again, we're going to have rate down here. I'm kind of cramming the units in, but it's the same calculation we did up there. But what we see now is that we expect the second half-life to be different. And the reason is because it has this concentration term in it. So in the first one, right, we have T1 half is equal to 1 over K times the concentration. So K is constant, but the concentration is changing as this thing, as this reaction kind of goes forward. And so in the second one, right, now our concentration is 0.005. And so we expect T1 half to be different because we're multiplying times a different concentration. And if we work that out, we end up with let's just call it that, 3,200. That's an S. Messy handwriting. So yeah, so the second half-life is 3,257 seconds, or yeah, 3,260 seconds or whatever. And so this, I mean, it might not make immediate sense, but if you think about it, we're saying if you think about normally for how like kinetics work, the higher if the reaction is concentration dependent, and you increase the concentration, then the rate speeds up. That's what we see from the normal rate law. Like if you think about the differential rate law or whatever, usually what we say is, I don't want to make this, like we wrote out the differential rate law for this. So this is not necessary to solve the problem, but maybe just to understand the context, right? We know that this thing's second order, so the rate law is this. What this tells us is that if the rate of the reaction is kind of how fast this reaction goes, right? Like how fast does this thing decompose or dimerize or whatever into CH12, that's what the rate is describing. How fast is this thing going to go? And what we see is that the rate is faster, at least the instantaneous rate is faster if C4H6 is higher. So the higher the concentration, the faster the rate. That's sort of the deal there. So it shouldn't be surprising when we look at the half-life that if the half-life is concentration dependent, we're going to see the opposite thing. So here we notice that the concentration is 0.01, the half-life is 1,630 seconds. As the concentration of this goes down, the reaction rate for it is also going to slow down. And what we see is that the half-life goes up. So it takes a longer time to go between 0.005 and 0.0025, 3,257 seconds, versus the first part, we're going to 0.01 to 0.005. So basically, all this is saying, like, I guess what I'm saying is the intuition here should hold up, which is that the rate is dependent on the concentration, and as the concentration increases, the rate gets higher, but as the concentration decreases, the rate becomes slower. And that's what we see here. This concentration has gone down from 0.005 to 0, from 0.01 to 0.005. And so we expect it to take longer for this half-life. And we'd expect the third half-life to be even longer still, and the fourth half-life to be even longer still, right? Yeah, so the other question is, if it was first order, everything is the same, we just use its respective half-life equation. That is mostly true. You definitely just use its respective half-life equation. First order is kind of interesting. Let me see if I can pull up a first order reaction here really quick. So let's say we've got I'm going to put the question in a different kind of context here. So, but does this make sense? So if you had to calculate the third half-life, for this reaction, you just do it again, we'd have T1/2, but now 0.025 is what goes into the half-life equation. So it becomes 1 over K times 0.0025. So the confusing part about doing the third and the fourth and the whatever fifth half-life is that, you know, we're not, A sub 0 is sort of changing with each one. So A sub 0 is like this initial concentration here. So fourth would be half of that, et cetera, et cetera. Second order, the half-life just doubles each time. So it feels like that would be true, that the half-life would just double each time. But it actually, well, does it just double each time? I don't know, I'd have to make a plot of it. The math is not immediately obvious to me. Is it 1630? Yeah, maybe you're right. Oh yeah, because let's see, so you are going down. Yeah, that might be true. Yeah, because you're multiplying by 0.5, yeah. 1/2, 1/4. So yeah, it's like a geometric, is that the geometric series? Oh good, okay, they put an LE on it, yeah. But this is the general idea, right? This is how this is coming. Yeah, if you have to calculate like 35 half-lives or something, you know, this is not a very practical way to do it. You'd have to use some sort of other equation to generalize it, but let's see. So for first order, so the key thing to take away when we come back and look at these half-life equations up here or one key thing to take away is that the second order half-life depends on the concentration that you have. But sort of the thing about the first order, oh my God, the thing about the first order, man, this Apple really wants me to update my software settings. First order reaction here does not depend on the concentration at all. There's no A sub O in this. So the half-life for a first order reaction is independent of the concentration. So if you're looking at a particular first order reaction, let's say like, about, let's say you're looking at this decomposition reaction. That's right. The concentration must be decreasing throughout the reaction, but what we'll see is that the half-life remains constant. Not necessarily the rate. The rate is going to still be dependent on the concentration. This is when I said earlier that first order is weird. I mean, maybe it becomes intuitive once you work with it for a while. Yeah, the half-life will remain constant. That's right. The rate will be dependent still on the concentration, but the half-life will not be, which to me is not necessarily, it's not immediately intuitive. But so if we have this reaction here and we're saying that it's first order, we could say it's first order, and we could say that K for the reaction is 6.93 times 10 to the minus 3 inverse seconds, and that N2O5, so our initial concentration, let me just call it initial concentration to avoid any kind of confusion there. Let's just say it's 0.1 molar. Doesn't really matter as much for this one. Okay, so same kind of setup, but the main difference here is that it's first order. So just somebody's question is like, well, what do we do? Do we just plug in for first order again? And the answer is like, basically yes. So the first order half-life is, so we're, sorry, the question we're asking here is, let's say, what is the first half-life? But yeah, so we take this equation and we just plug in the values to get the first half-life. But you'll notice that there's no concentration term in this. And so the half-life is only dependent on the rate constant. So what's the half-life here going to be? It's going to be 0.693 divided by 6.93 minus 3. Yeah, this one's nice because it works out to just be 100 seconds. And so what's the second half-life? So this is, so let me be explicit about it. So this is the amount of time it takes me to go from 0.1 molar N2O5, and I'm going to 0.05 molar N2O5. How much time does that take? It takes 100 seconds. And then, so that would be our first half-life. And then, so then our second half-life, we're going to say, okay, well, we're going 0.025, 0.05. You know, how long is it going to take us to go from that to 0.025 molar? And the answer is, it's just going to take 100 seconds again. Because if we come back up here and look at our equation, there is no concentration dependent. So every single half-life for the first order thing is always going to be 100 seconds. So that's different from what we saw in the last one. So that means that also going from 0.0025 to 0.00125 or whatever. Yeah, natural log of 2, 0.693, those are equivalent. So, you know, and I'm not looking at your work, so yeah, so I would just use 0.693. Like if you want to play around with if you want to be a little fancier with kind of how you're learning it, you can derive the half-life equations yourself every time. But yeah, when you're trying to solve problems on an exam or something, use the simplest thing possible. But yeah, so here our second half-life is just 100 seconds. Our third half-life would be 100 seconds. Our fourth half-life would be 100 seconds. And so what we see that for first order is that the time is not dependent on, the half-life time is not dependent on the concentration at all. Whereas up here, because we have a concentration term in the half-life equation, we see that that's not the case. You know, in order to go from 0.01 to 0.005, it took 1/1600 seconds, give or take, and then to go to the next one from 0.005 to 0.0025, now it's going to take over 3,000 seconds. And so we see that the half-life kind of decreases as the concentration decreases. Zeroth order, we also see that there's a concentration term in there. Where is it? There it is. Zeroth order, we see there's a concentration term in there as well. So again, we expect that the half-life will change depending on what the concentration is, the initial concentration is. Okay, so the last little bit on the first order stuff is just that, or sort of a nice thing, a nice gift from nature, because nature tends to be extremely complicated, is that, I talked a little bit about this already, but that radioactive decay processes are always first order. So radioactive decay is, did we learn about nuclear chemistry in the first? I can't remember when maybe we learn about that first semester. It might depend on who you take. But radioactive decay would be like if I've got one isotope, so it's not chemical reaction in terms of, you know, I'm taking reagent A and combining it with reagent B. These are actually like elements that are decaying into other elements. So we start out with uranium-238, and over some amount of time, it's going to go to lead-206, for example. So it's going to emit some sort of radiation. It's going to lose some protons and become lead. So these are things that are happening in the nucleus of the element, which is different from what we're normally looking at. But so the nice thing, what this allows us to do, because it's not concentration dependent, is it makes it very easy to figure out the dates of things. So carbon dating and carbon dating is probably the most common thing that we do, right? That's dependent on these radioactive decay processes. And if you know the half-life of it, of whatever the element is that you're looking at, you can kind of back calculate how old, for example, a sample is. So if you have like a tree or something that's been fouled, that you find out in the middle of nowhere, you can cut that down. And you can take a sample of that back and look at the ratio of the isotopes and stuff in there and figure out how old it is. That's all based on this idea of half-lives. But any kind of radioactive decay process, so anything involving decay from one element to another, is going to be first order. So for example, this one is nice. Uranium-238 goes to lead-206. The half-life for this is 4.5 billion years. And so anytime you're given a first order, so you could be given something that's a radioactive decay process and told, you know, what its half-life is, or that's probably the most, or it could say like, I start out with, yeah, so for example, it could say like, let's say we have 100 grams of uranium-238. How long I'm trying to think about how you could phrase this that doesn't require, that you wouldn't use the integrated rate law for. I guess you know T1 half. Yeah, there's a bunch of different ways to solve this. You could say like, let's start with an easy one. Let's say we have 100 grams of uranium-238. Yeah. How long will it take to decay to 50 grams uranium-238? So this is like the most straightforward this question can be. The half-life is literally that time. So if you start out, like, let's say you find a rock, this is how we know this is how we know how old the Earth is. You have these rocks that are started out as pure uranium-238. And if we look at them today, because it's been about 4.5 billion years since the planet formed, what we find is that we have only half of that left over, and the rest of it has been converted over to lead-206. And so how long will it take to decay to 50 grams? Yeah, it's going to take 4.5 billion years. So this is kind of how the radioactive decay problems look. There's a million different ways you could ask these types of things, but ultimately they just fall back. They ultimately just fall back on this idea of using first order reaction stuff. So you could also say, like, what are some other things you could ask? You could say, like, what is K? For this decay process. And since we know that T1/2 is equal to 0.693 over K, and we know the half-life, we can say, well, okay, we know that K is going to be equal to 0.693 over 4.5 billion years. I should write that out, not as billion, but and so, yeah, so what does K end up being? Some really small number. Oh, not times 10 to the 9 is 9. Times 10 to the 9th, positive 9. And so we see that K for this is 1.54 times 10 to the minus 10th. And so then, you could use that to answer questions about the integrated rate law, for example. Yeah, like if it said, like, well, I don't know. I'm trying to think. You can imagine the types of questions that you could come up with, though. So yeah, we can calculate K. Let's see. We know the half-life of this. What's some other ways that we ask these types of things? Let me pull a question really quick. I usually pull these out of my head. I'll get 2 minutes. Perfect. Some of these are just so annoying. Some of them are annoying because they have they'll make you go through like these mole calculations or something. But here's one that I've just pulled randomly off the internet. So it says, like, the half-life of zinc 71. So they're not even telling you what it decays to. They don't care. It's just telling you the half-life is 2.4 minutes. Yeah, if the initial concentration or initial amount, I guess it doesn't make sense necessarily to talk about in terms of, I guess that's one difference for these. So when you're talking about radioactive decay, you're not usually talking about concentration, you're talking about mass. If the initial amount is, I don't know, I'll change my thing up from there at least. Let's say at 172 grams. How many grams would be left? I don't know, let's say after 1 hour. Yeah, so if we want to figure this out, let's see what we need to use here. There's a couple of different ways we could do this. Probably the easiest thing to do is to say, let's say we know this is a nice. Okay, so I think for first order, since it's first order, the nice thing about these is a good problem. Since first order, the nice thing you can do with these is we can calculate the number of half-lives, so in 1 hour. So sort of the sub-question here is how many half-lives are in 1 hour? So 2.4 minutes is the half-life. So for example, if you had 4.8 minutes, that would mean that you would have 2 half-lives within 4.8 minutes. So how many in 1 hour? So we take 60 minutes. And divide it by 2.4 minutes. And this is going to give us the number of half-lives that this thing goes through over the course of 60 minutes. So 60 divided by 2.4. So it's 25 half-lives. So then if we want to figure out how much is going to be remaining, we would take and say, okay, it's going by a half. So it's going by a half. So I'm trying to think of the way to explain this. So if you were going through 1 half-life, it would just be, you would take 1/2 and multiply it times 172 grams. So like right after think about it like this. If we're starting out with 172 grams, after 2.4 minutes, we're going to have exactly 1/2 of that. So this little math equation that I wrote here would describe that perfectly. This is exactly the amount that we would expect after 2.4 minutes. If we were to then say, well, what happens after 4.8 minutes? What would we do? We'd multiply it times 1/2 again. If we were to say, well, what happens after, let's see, 4.8 plus 2.4 is what? 7.2. So after 7.2 minutes, so 3 half-lives, what's that going to be? We're going to multiply it times another 1/2. So each time it's going by a 1/2. And so the amount that we'd have left over is 1/2 to whatever the number of half-lives is. Since it's halving each time, we can use this nice simple equation. And so in this case, I'll leave that there. In this case, it'd be 1/2 to the 25th times 172 grams. So we're going to get a very small number here. So we end up with, a teeny tiny fraction of what we started with after 1 hour. Yeah, what if this was second order? That's a good question. We are out of time in class. We can pick up and talk about that. Oh, bunch of questions. Yeah. Okay, so one important note somebody's asking is they'll tell us what the order of the reaction is. Generally speaking, we do. We don't have to tell you that if it's something involving the half-life of radioactive isotope. So if it's a radioactive isotope where it's a decay process, oh, I'm sorry, I'm going way too far back. But if it's a radioactive decay process, then you know it's first order. Nobody has to tell you. The time doesn't really matter. You just want to make sure you're consistent in terms of what your units are. So for example, up here, right, when I calculated the K value for this, it's in inverse years. It's just, you just want to be consistent. And then the last question is, what if this was second order? Yeah, we'd need to describe this differently in terms of figuring out the half-life. So we'd have to look at some power of the, I'll have to think about that. But yeah, there's some way to do it with the second order too, I'm sure. But for the first order, you can see why these are really nice. Because it's just a very simple equation. It's just 1/2 raised to the number of half-lives times the concentration gives you the final concentration. And you can see that for any particular thing, eventually the concentration tends towards zero. So, the limit on this thing is it's going towards zero. So 5.12 times 10 to the minus 6 grams, a teeny tiny amount. After like 2 days or something, there's basically none of that left, right? Anyway, so all right, so that's half-lives. Yeah, we might talk a little bit more about that when we get to class on Friday, and then I want to jump into reaction mechanisms because those require a little bit more of analysis. But hopefully this gives you a good handle on how to deal with these things. Yeah, all right. I'm going to take a break, look at the election results, and drink some water, and then I'll see you guys in office hours.
Can I ask why you don't need to change the K for the N2O5?
Sorry, could you say that again?
Up
here?
Yeah. Why you don't change here T?
Why don't I change K?
No, well, I mean, why do you don't change T?
Why don't I change T? Because this is so for first order, T1 half doesn't change. That's sort of the whole deal with first order reactions. So if you just think about it, just forget about the idea of first order and stuff, and just look at the equation for first order reactions. We have this equation. And so what we see is that, we've got K, which is a constant. So obviously that's not going to change. And then in the numerator, we have 0.693. So it doesn't matter what the concentration is that you have, the half-life is always going to be the same. So if I give you 100 molar or a 10 molar solution, the half-life is going to be exactly the same regardless. So it just kind of falls naturally out of the equation. So each jump from one concentration to half that concentration always takes 100 seconds, independent of what the starting concentration is. And that's what we see down here. If we look at like uranium-238, here I started with 100 grams of it, and I know it's going to take 4.5 billion years to become 50 grams. But if I started out with 1,000 grams of this, or 50, let's say 1,000 grams, it's still going to take the same amount of time to go to 500 grams. It's independent of the concentration. Second order, on the other hand, this one feels more intuitive to me at least, which is that the half-life is dependent on the concentration. And that's what we see here. When we look at the half-life equation, we have a concentration unit in the denominator. So yeah, K doesn't change. That part is consistent, but A sub 0 is constantly changing. And so the half-life is also changing as well. So I don't work with half-lives a lot, but like a half-life for a second order reaction or a zeroth order reaction is a much less useful equation maybe compared to the first order ones. This is really where this equation really comes in handy as a description, because we can describe so much about what's happening in the chemical reaction with just this one number. We can say, okay, it takes 100 seconds to go to half, regardless of what the starting concentration is. Whereas up here, it's specific to what the starting concentration is. So. Yeah.
Can we look at question number 3 in LE 3.05?
Got it. Let me go to Canvas real quick. Okay, so LA 3.05, we're looking at integrated rate laws here. And we are looking at question number 3. Okay, so we're looking at this decomposition reaction. All right, so this question says the reaction gives us this reaction. And it tells us that we have a reaction rate is only dependent on the concentration of N2O5. Okay, that would make sense. And at a certain temperature has a rate constant of 0.0168 per second. If 2.5 moles of N2O5 were placed in 5-liter container at that temperature, how many moles of N2O5 would remain after 1 minute? Let's see. So what do we need to do here? So we know K. So I think this is one of the ones, I think somebody pointed this out in class or in office hours or something. We know K is equal to 0.0168 inverse seconds. And we know that the rate is going to be equal to K times N2O5, raised to some power over here. So, the first step usually the first step in these questions is figuring out what the order of the reaction is. And ordinarily you're given experimental data that tells you that. This one is strange in that it doesn't give you experimental data, but it does give you K. And so we can figure it out from K, I believe. Let's see. So K is in inverse seconds. Let's see. K is in inverse seconds. And we know that the rate of the reaction should be in moles. Yeah, so the units on the rate are always in, well,
I think when it's in only inverse second, it's for first order.
that's right. I think I kind of missed a little bit what you said there. Were you saying that because it's in inverse seconds, we know it's first order?
Yes.
Okay, good. So you're there. That, to me, that was what I thought was going to be the confusion point on. Okay, so it's first order, so good. And then it's just saying if we have 2.5 moles in a 5-liter container, how many moles would remain after 1 minute? So what do they want you to do here? 2.5 moles in a 5-liter container. Yeah, I mean, I think we can write that out in molarity, no problem. So we can say that N2O5 initial is just going to be equal to 2.5 divided by 5. So 0.5 molar. And then it's asking about what that concentration will be at time t. That's sort of this is what we're looking for. And then, yeah, it's giving us t. So it's saying t is equal to 1.00 minutes. And then it's also giving us our k value. So it gives us a good amount of information here. And so, yeah, so what do we want to do here? Calculator out. We're going to use our rate law for first order reactions. So since we know it's first order, we know that natural log of A is going to be equal to negative KT plus natural log of A sub 0. And let's see, then we're solving for N2O5, so we should plug that in. So we should end up with N2O5 sub T is equal to e to the negative kt plus the natural log of our initial concentration, which is just 0.5. Well, let me be consistent here. I haven't put any numbers in yet. Is this how you worked it, Taylor? Did you just would it just not take your answer?
I received was incorrect, but I used the first order, the natural log. I'm just seeing. The answer I put in was wrong, so I'm just trying to see where I went wrong.
So you're working it correctly. Sometimes whenever I make this, like for your exams, so I didn't make the LEs. So some of the other instructors made those. I don't even know when. Must have been like 4 or 5 semesters ago. But I try to avoid having the numerical ones just because sometimes they can just be wonky. If you're off by a little bit because of significant figures or rounding, that's why we always do multiple choice in exams. Let's see what I get. So the correct answer, I'm looking at it, says 0.912. That's the acceptable one with the error margin of 0.01. So I don't know if you came out with something around that. Let's plug in some values here and see what we get. If I get the same thing. So we'd end up with e to the negative 0.1, 0.168 inverse seconds times our time, which is 60 seconds. I hate when this happens. Plus the natural log of N2O5, which is 0.5. And so let me punch that in my calculator really quick. Did not get their answer. Let me try one more time.
I've been getting 0.182. Is that?
Yeah, that's what I came out with as well.
Okay.
Well, let's see. So either they're wrong or we're wrong. So let's see what we get. So 0.182. Of course, there's no explanation. Let's see. Where the hell are they getting 0.912 from? Has a reaction that is only on the concentration at a certain temperature as a rate constant. If we're using the right rate constant. Our initial concentration is correct. It's 2.5 moles in a 5-liter container. It's going to be 1/2 molar. It's asking. It's asking. So this is. What a silly thing. All right. So this is equal to 0.182 molar. It's asking how many moles. That's all it is. This is some silly. Does that make it clear now what the answer is, though? So
now I feel dumb. I need to read the question.
I made the exact same mistake and then had to reread it, so don't feel bad. Okay. So yeah. So then you just solve for whatever that is. I'm sorry, in 5 liters. Yeah, so then it's just 5 times that. So 5 times 0.182. And yeah, that gives their answer. So yeah. Yep.
Thank you.
Yeah, you're welcome. This is one of the things I don't like about the like chemistry in general at the introductory level is like, it's just this kind of like weird unit situation that you end up in. It just gets super confusing sometimes. All right, so Athena, yeah, if you got the right answer and did not do the last part. Wait, so you came out with the right answer of 0.912, but did not do the last part. That means that you probably did not use, let's see. Did you just not divide by 5 liters in the first place and just started out with 2.5 moles? Yeah. Let's see, should we expect that to work? I guess that's fine. Yeah, I guess let me think about that. Yeah, I guess that works. That's not my instinct to do it that way just because I usually work in concentrations, but because you're first order in one reactant, that should work. I don't know. I would generally work with the concentration and then back the number out. I'm trying to think of why I would always do that. So I guess, I think for a first order reaction, you can get away with that. If it's first order in a single reagent, but if it was second order, then you would run into problems doing that. So you'd want to make sure you go into concentration. Because the first order, I guess this is why it makes sense that the half-life for the first order reaction doesn't depend on the concentration. This sort of points towards that. That's why it works for you guys. So I guess what I'm saying to those of you who worked it out and got it because you just didn't divide by 5 is that, well, that's fine, but it will only work for a first order reaction. So the rate of the reaction, so for these, like if you think of a chemical reaction as happening, this is maybe probably going overboard in terms of explanation, but like, so if you have a reaction like this, let's say that the black dots represent N2O5, just spontaneously, regardless of where they are in space, they're just naturally going to go and convert to whatever the product is. Like there's no reaction that happens. They're just kind of vibrating, and eventually they just vibrate to the point where they become something else. But if you look at a second order reaction, second order reactions will have, let's say you have 2 reactants in there. I don't know, this makes it clear to me. I don't know if this is actually a good explanation to give to you guys, but in a second order reaction, like the reaction actually happens because of collisions between the molecules or atoms in the flask. So if the probability of like a red and a black molecule combining or knocking in each other and producing a product is going to change as the size of the flask changes. So like as the flask gets bigger, it's like this, the probability of the red and the black dot running into each other becomes smaller. So your reaction rate becomes dependent on your concentration. I don't know. I guess the short answer that I should have just stuck with in the first place is that what I'm saying here is correct. I just know it's not very clear what I'm saying. The short answer is that for first order, yeah, if you just use moles, it's fine. For second order, if you try to just use moles and skip it, you would end up in trouble there. You would have problems with that. So just just pay attention to which order of the reaction it is. When we talk about reaction mechanisms, the little diagram I just drew maybe will make more sense, but yeah. Yeah, because we haven't really talked about that at all. But yeah, for like a first order reaction, you're typically just looking at like a vibrating molecule that eventually just kind of like, spontaneously vibrates and breaks apart. So concentration doesn't matter. Let's look at question 1. The rate constant for the decomposition reaction of, let's see. Are you guys finding this material to be a little bit easier than the acid-base stuff?
Yes.
Yeah, I think it is too.
On the last question, did you just know the order because of the units that it gave you?
That's right. Yeah, somebody asked about that in class, and my response was, I don't know why you do that, but yeah, I get, since it's a learning exercise, Yeah, they just give you the units here. And that the thing to remember is just that the units on rate are always in, but they'd be in like mole liter per second. Something like this. So K has to work out such that the units on the rate come out to look like this. So we know that N2O5 is going to be in moles per liter because it's a concentration thing. And so if we know that K is in inverse seconds, that tells us whatever X has to be. That's the way to do that. But usually if you know K, the way these are set up is like, a lot of times is like you're the experimentalist, like you have this experimental data and you're trying to figure things out. If you know K, you have to know the order of the reaction. So it's not exactly how you would deal with things. It doesn't make sense from an experimental point of view. Like, why would you know K and then have to deduce the order of the reaction? But yeah, Athena, I'm not saying, I don't want to use the term bad strategy. I'm just saying it's a strategy that will only work for first order reactions. So generally you want to work, if you look at the, yeah, let me just leave it at that. It'll only work for first order reactions. So in a second order reaction, if you ignored the 5 liter and tried to work it, you would come out with the wrong answer, which, if we were doing open, like free response questions, that wouldn't be that big of a deal. But on a multiple choice exam, it can be the difference between getting it right or wrong. And honestly, it wasn't obvious to me that was true. So it's not until I kind of sat down and thought about it, until you asked the question, I guess. Okay, so it would be different for second order because this is what I started to explain and was doing a really shitty job at. It's just different for second order because, let me think if there's a way to explain it with the equations and not using some chemical intuition.
I think it's because first order is constant while second order isn't constant.
First order is constant.
Like at the rate of change for first order, it's like always the same. Like in terms of K.
Rate of change is always the same. Like the instantaneous, well, that's not really true though, because at least maybe when you're like in the instantaneous rate is going to change with the concentration, like as the concentration changes, the rate is going to change. Sorry, I'm trying to, maybe I'm not understanding what you're saying. Let's see. Rate of change. I had a thought about this earlier, why it didn't matter. It doesn't make sense to me looking at the equation, even though it probably should. To me, it makes sense that it doesn't depend on the volume, just because for I guess the way I usually think in terms of pictures, but like in terms of like a chemical intuition as far as what a first order reaction means. Let's see, what does it mean over here? God, I really want to be able to say something intelligent about this. So we've got rate, we've got K, we've got this, and we're saying we're looking at the differential rate, the integrated rate law, so maybe look at that instead. They're all linear. Versus. It might hold true for a second order reaction. No, my intuition is like it can't hold true for a second order reaction. Let's just say let's not worry about why that's true for right now, because I don't want to get off and make you more confused. It's not immediately obvious to me out of the math, and I'd have to work through it. It'd probably take a long time and probably not be super helpful for you guys. So I guess my instinct as far as like why it's true is just that. So in a first order reaction, let's see if I can keep this concise. In a first order reaction is, you have A and it spontaneously goes to some product P. And so if you think of just think of A as being, let's just draw a cartoon for the the molecule. So let's say you have two atoms that are connected to one another by a spring. In a first order reaction, what's happening, and we'll talk a little bit about this on Friday, in a first order reaction, what's happening is like, usually what's happening at least, is this thing is vibrating a lot. And then just spontaneously, so you know, these arrows here are showing that the spring is kind of vibrating. So there's kind of like if you've taken physics and you talk about Hooke's law and stuff, that's kind of how you can imagine this. This thing is vibrating back and forth. Spontaneously, what will happen is, like, let's say it just breaks up into two atoms. So eventually, you know, if you stretch a spring far enough, it'll just break, and that's what happens here. So that's basically what a first order reaction, that's what happens in a first order reaction. So whether or not I have like one molecule of this or 10 molecules of that, it doesn't really matter, right? They're just going to vibrate, and eventually the vibration is going to lead to this thing breaking apart. And so that's why in my mind, it doesn't matter. Like if I take this, let's put it this way. If I take this one molecule and I put it in a box like this big, or I put it in a box this big, it doesn't matter, you know, like it's still going to vibrate with the same amount of energy, and the probability of it breaking apart is going to be the same regardless of the size of the box. This will make a little more sense when I show you what happens in a second order reaction. So in a second order reaction, let's say I have the opposite thing. So in this top one, I'm looking at a decomposition, but in a second order reaction, let's say we have something that's combining. To make a molecule. So now it's like they have to come in contact to form that little spring. So if the box is really small that I put them in, so the box is the concentration, right? So concentration is a function of the number of molecules that I have per like unit volume or something. So as the volume of this grows, the concentration goes down. And here it's kind of silly because I have one molecule, but the idea holds. But you know, so if the box is really small, so my concentration of these two things is very high, the probability, so in order for this reaction to happen, these two molecules have to bounce into each other. It's like this one has to approach that one, and that one has to approach that one, and they have to just sort of collide to each other in a way that makes it productive, and now a bond forms between them. But in order for that to happen, obviously they have to bump into each other. So if the box is really small, the probability of them knocking into each other is really high. But as the box gets larger and larger, that probability gets smaller and smaller. So like now it's much easier for them to stay apart. And as the box gets larger and larger and larger and larger, the probability gets smaller and smaller and smaller. So the reason this is related back to the original question, though, is that if you just look at the number of moles, you're saying that the size of the box doesn't matter, because 1 liter is essentially the size of the box. So if you're just looking at the number of moles, we're saying, well, it doesn't matter what size the box is, it only matters how many moles are around. And that's essentially saying that the concentration doesn't matter. And that's true up here in a first order reaction, because as the box gets bigger, I'm not dependent, these two atoms are like stuck together. So I'm not dependent on the size of the box kind of forcing them into contact. They're going to remain in contact no matter what. There's no probability of them bumping into each other. I don't care about that. But down here, it's like as well as the box gets bigger, now the probability of these two guys colliding with one another gets smaller and smaller. So the concentration does matter. That is my instinct as far as like why first order is going to depend on is not going to depend on concentration, and second order will, and third order also will. So it just depends on how the molecules come together. But this thing here that I'm saying is true, and we're going to learn about this in more detail on Friday, which is this, that in a reaction mechanism, all this crap that we're talking about, like all this mathematical modeling that we're doing with order, is related fundamentally to what's happening at the atomic scale, which is like things have to bump into each other for a reaction to happen. or, you know, here things have to split apart for reaction to happen. So we can actually say something about what's happening at the microscopic level. In a more general sense, like in terms of just looking at the math to figure out why a first order reaction doesn't depend on the concentration, I have to think about that more. But this is how I think in terms as a chemist. So I don't know how helpful that is. Oh, good. Okay, that helped a lot. Thank you. Okay, let's look at question 1 here. So it just says the rate constant. Oh, okay, yeah, these always throw people when there's a percentage in there. It just says the rate constant for the decomposition reactant A is 0.0092 seconds. So it's saying A is, you know, decomposing to whatever, we're going to call it B. We know that K is equal to 0.0092 inverse seconds. Man, they really get you with these K values where you have to deduce what the order of the reaction is. But how long will it take for 80% of the reactant to decompose? And please answer in seconds. So the trick for these, so the question is how long for 80% of the reactant to decompose. Yeah, so, you know, I assume you can only, again, I think I'm learning, every time I reteach general chemistry, because my PhD is in organic chemistry, I always think a little bit deeper about this PChem problems. But I think this would probably, these types of questions probably only can be asked of first order equations, or first order reactions, because as we just kind of said, first order reactions don't depend on the, is that true? Could you do it for a second order? I don't know, I'd have to think about it more. But my instinct is it can only be first order, but we know it's first order anyway, because the units over here are just inverse seconds, and we just worked through why that's true. So this units tell us it's first order. And then it's just asking how long for 80% of the reactant to decompose. So to do this, you just set, we're going to use the same equation that we used before, which is this natural log of A t is equal to negative kt plus natural log of A sub O. So that, you know, the one confusing thing here is that we don't have values for these, but it's asking us how long for 80%. But what you can do is you can just plug in fake, like imaginary values. It doesn't matter. So 80% of anything will give us the correct answer here. So we can set A sub 0 to some arbitrary amount. It makes sense to just set it to 100 because that makes the math easy. And we want to know how long before 80% of it is decomposed. So that means that at whatever time t is, when 80% of A sub O is gone, that means that we'll have only 20 left over. And then we can just solve for that. So what would that end up looking like? We'd end up with natural log of A sub t minus natural log of A sub O divided by negative k is equal to t. And then when you plug in your values, what do we end up with? Actually, I'll just cheat and look at their answer. So, yeah, so 175. Yeah. That's how those work, though. You just have to make up a number. So if it's asking for percentages, just call A sub O 100 and then call A sub T, you know, the whatever it's asking about. So if it's saying 80% decomposed, then 20 is the number we're going to plug in there. Let's see, second order reaction, would that work? Yeah, I guess it would work for a second order reaction because they're, yeah, it would be fine. it's the half-lives for second orders that get a little bit weird. But yeah, like all of these questions, so there's like a larger diversity of questions you can ask around kinetics. But it's just kind of like, to me, what it ends up looking, from a student perspective, like there's just like tricky type things. Like, yeah, okay, so if they don't tell you the order of the reaction, they don't give you anything, you have to deduce it from K. Or like, I don't know, that last one that we worked on where it's like they're asking for the answer in terms of moles versus molarity. That one's particularly strange. So with respect to everything that we've done up until now, it's the questions are reasonably straightforward. They can be asked in a way that makes them a little bit confusing, but generally the workflow is the same. Figure out the order of the reaction. And then usually you're using the integrated rate law. The differential rate law, which is, this thing where you just set the rate equal to K times A, is less useful because it's like, there might be a question on the exam or some questions on the exam about it, but like it's unusual that you would be curious about the rate at a particular point in the reaction, which is what this relates, right? It's like, okay, well, when the concentration of A is something, what's the rate of the reaction to be? Who cares about that? What I really care about is, when is the reaction to be over with? And that's what these types of questions pertain to, how long until 80% of the reactant decomposes? So you can imagine like an example of that might be like environmentally, if you have some like pollutant in the ocean, like some PCB or something, these chlorinated aromatic compounds, and you want to know how long it's going to, you want to know something about it. Usually what you're worried about is like, well, when is this stuff going to be gone? How long is this going to stick around in the ocean for? Or like plastics, when people talk about that, it's like, how long is it going to be before plastic decomposes completely? And, that's why the integrated rate law is so important, is because that's the type of stuff you can say with it. You're trying to relate concentration to time. And so you could use maybe not a first order thing, but you could use something like this to model how long plastic would be on the planet. Whereas if we look at the differential rate law, it's like, what can you really say about the plastic? Well, we could say like at a particular concentration, what's the rate of decomposition going to be? But like, that's just not as useful of a thing. So, any other questions? Let's look at those election results. God, this is an insanely close race. Michigan right now is 96% reporting, 49.5 for Biden and 48.9 for Trump. Georgia's 50.5 Trump, 48.3 Biden, 94% reporting. Looks like Biden's going to probably take Wisconsin. I don't know. It's interesting to look at the election results in terms of data skew. Like if you watch the election, I don't know how you guys maybe are too young to care. I'm not sure. But if you watch how the data comes in, it's like initially it looks like the Democrats are like, going to win in a landslide, but it just has to do with how they count the ballots. So then suddenly it's like, okay, now the Republicans are coming back, but now they're counting like later ballots. So the absentee ballot. So now it looks like, the Democrats are making comebacks. So you kind of see this thing. I guess in terms of chemistry, you can think of the final results of the election being sort of the thermodynamic. Once the election hits thermodynamic equilibrium, it's just kind of the static number of like Biden got this many votes and Trump got that many votes. But if you're thinking in terms of kinetics, it's the actual path there, and you can kind of see that, in terms of like the number of votes that Biden gets and then the number of votes that Trump gets, like that's constantly changing throughout time. And that's sort of the path that you're taking to kind of get to the final election results. It doesn't affect what the final election results are, but it does affect kind of how you think about the election at any point in time. And that's kind of what chemical kinetics are. We can look at these equations and say something about a particular reaction at a point in time. But if you look at if you look at the overall reaction, it doesn't really matter what the path is if all you're worried about is making, for example, N2O4. You're going to get there eventually, and the path doesn't really matter. So that's sort of the difference. Anyway, I need to, this is what happens when you're a chemist. Everything becomes kind of interrelated, or whatever you end up majoring in, everything starts to come into focus in that same lens. Okay. Do you guys have any other questions? If not, I'm going to wring my hands and watch the election results. This is the most, the closest reaction. The closest reaction, Jesus. This is the closest election I think I've ever seen. And with the polling errors and things, it's become quite interesting to watch. Anyway, all right, I will see you guys in class on Friday, and hopefully we at least know who the president is at that point in time. And just remember, I guess we have an exam next week, so I need to get on top of that. Bye, you guys.